Close your eyes for a moment. Take a deep breath. Feel the weight of your body settling into comfort, the tension draining from your shoulders, from your neck, from every muscle that's been carrying you through the day. In this moment, there's nowhere you need to be, nothing you need to do. You're about to embark on a journey unlike any other. A gentle drift through the vast expanse of our solar system, where time moves slowly, and peace is found in the infinite stillness of space. Imagine yourself lifting away from Earth, not with the violent thrust of a rocket, but with the gentle float of a feather caught on a soft breeze. The pull of gravity loosens its grip, and you find yourself suspended in the velvety darkness of space, surrounded by countless points of light that have been shining for billions of years. Here, in this cosmic sanctuary, there are no deadlines, no responsibilities, no noise except the profound silence that fills the void between worlds. Our solar system is a place of remarkable order, hidden within apparent chaos. A cosmic dance that has been choreographed over 4.5 billion years. 8 major planets orbit our Sun in near-perfect harmony, each following its own elliptical path through space, never colliding, never deviating from the gravitational patterns that hold them in place. Between and beyond these worlds lie countless smaller bodies, asteroids and comets and moons, all moving in their own peaceful trajectories through the darkness. What makes this journey special is not the destinations themselves, though they are spectacular beyond description. It's the spaces between them, the vast distances that remind us how small our worries are, how temporary our troubles feel when measured against the scale of cosmic time. Out here, 1,000,000 years is but a moment, and the planets themselves are children compared to the ancient light of distant stars. As we begin this tour, there's no need to hurry. We have all the time in the universe. We'll drift past each world slowly, observing without judgment, appreciating without analysis, simply experiencing the serene beauty of our cosmic neighborhood. Each planet has its own character, its own peaceful presence in the solar system, and each offers us something different to contemplate as we float through the darkness. The temperature of space itself hovers just a few degrees above absolute zero, but you feel neither hot nor cold. Out here, beyond the concerns of terrestrial life, you exist in perfect comfort, free from the constraints of physical form, able to observe and appreciate without the distractions of sensation. You are consciousness itself, drifting peacefully among the planets, a silent witness to the majesty of creation. Let your breathing slow even further as we prepare to visit the heart of our solar system. Feel yourself becoming lighter still, more transparent, as if you're dissolving into the starlight itself. This is a journey of the mind and spirit, a meditation on the scale and beauty of the universe we call home. And it begins, as all things in our solar system must begin, with the Sun. The Sun, our cosmic anchor. In the center of our peaceful system blows a star, massive beyond comprehension yet appearing so small from distant worlds. The Sun dominates our solar system in every measurable way, containing 99.86% of all the mass in the entire system. Everything else, all the planets and moons and asteroids and comets combined, make up less than 0.2% of the solar system's total mass. The Sun's gravitational influence extends outward for light years, holding everything in its gentle but unbreakable grip. From this close perspective, Floating at a safe distance where we can observe without being overwhelmed, the Sun appears as a sphere of brilliant golden light, its surface bubbling and churning in slow motion like a vast ocean of plasma. The photosphere, as this visible surface is called, reaches temperatures of about 5,700 degrees Celsius, hot enough to vaporize any known material instantly. But from our vantage point, separated by the vacuum of space, it appears almost gentle, a warm glow that has nurtured life on Earth for billions of years. The Sun is not uniform in its brightness or temperature. Look closely and you can see darker patches scattered across its surface, cooler regions known as sunspots that appear and disappear in cycles lasting about 11 years. These sunspots are still incredibly hot, around 3,800 degrees Celsius. But they appear dark only in contrast to the surrounding brilliance. They're created by intense magnetic activity within the Sun, temporary disruptions in the flow of heat from the core to the surface. Beneath that glowing surface lies the Sun's true power source, a core, where temperatures reach 15 million degrees Celsius and pressure becomes almost incomprehensible. Here, in this stellar furnace, hydrogen atoms collide with such force that they fuse together, creating helium and releasing tremendous amounts of energy in the process. Every second, the Sun converts about 700 million tons of hydrogen into 695 million tons of helium. The missing 5 million tons of matter are transformed into pure energy, the light and heat that travels outward to warm the planets. But this energy doesn't travel directly from the core to the surface. Instead, it begins a slow journey outward, taking hundreds of thousands of years to work its way through the dense interior of the Sun. In the radiative zone, photons of light bounce endlessly between particles, each collision sending them in a new random direction, gradually working their way outward in a drunken walk through the stellar interior. Eventually, they reach the convective zone, where heat rises in great columns like bubbles in boiling water, carrying energy toward the surface. When that energy finally reaches the photosphere, it's released into space as the light we see and the warmth we feel. It takes only 8 minutes for sunlight to cross the 93 million miles from the Sun to Earth, traveling at the speed of light through the vacuum of space. This light has sustained life on our planet since its beginning, driving photosynthesis in plants, warming the oceans, creating weather patterns, and making Earth the vibrant, living world it is today. The Sun's atmosphere extends far beyond its visible surface. Just above the photosphere lies the chromosphere, a thin layer where temperatures actually increase with altitude, reaching about 8,000 degrees Celsius. Here, hydrogen gas glows with a distinctive red color that can be seen during total solar eclipses. Beyond that lies the corona, the Sun's outer atmosphere, where temperatures soar to over 1 million degrees Celsius for reasons scientists are still working to fully understand. This superheated outer atmosphere streams away from the Sun in all directions, creating the solar wind, a constant flow of charged particles that fills the entire solar system. The Sun is classified as a G-type main sequence star, often called a yellow dwarf, though it actually appears white when viewed from space without the filter of Earth's atmosphere. It's neither particularly large nor particularly small among stars. There are stars hundreds of times larger than the Sun, massive giants that burn through their fuel in mere millions of years before dying in catastrophic explosions. There are also stars much smaller than the Sun, dim red dwarfs that will burn steadily for trillions of years, long after larger stars have exhausted their fuel and faded away. Our Sun is middle-aged, about 4.6 billion years old, with roughly another 5 billion years of stable hydrogen burning ahead of it. It formed from a cloud of gas and dust that collapsed under its own gravity, the same cloud that gave birth to all the planets. As that cloud collapsed, most of the material fell toward the center, forming the proto-sun, while the remaining material flattened into a disk from which the planets eventually coalesced. One day, billions of years from now, the sun will begin to change. When the hydrogen in its core is exhausted, the core will contract and heat up, causing the outer layers to expand. The sun will swell into a red giant, growing large enough to potentially engulf Mercury, Venus, and possibly even Earth. But that day lies so far in the future that it's almost beyond comprehension, separated from our present moment by millions of human lifetimes. For now, the sun burns steadily, a beacon of warmth and light in the cosmic darkness, the gravitational anchor that holds our entire system together. Its presence is reassuring, constant, a reminder that even in the vast emptiness of space, there is order and stability. As we float here, observing its golden glow, we can appreciate the sheer power contained within its volume power, that is carefully balanced and controlled by the laws of physics, never running wild, never destroying the delicate dance of planets that surrounds it. The sun's magnetic field extends throughout the entire solar system, creating what's known as the heliosphere, a bubble of influence that protects the inner planets from much of the harsh radiation of interstellar space. This field is constantly being carried outward by the solar wind, creating a dynamic, changing boundary between what belongs to our sun and what lies beyond in the galaxy. From our peaceful vantage point, we can see solar prominences, great arcs of plasma that leap from the sun's surface, following magnetic field lines high into the corona before falling back. These can stretch for hundreds of thousands of miles, dwarfing the Earth in size, yet they appear graceful, almost balletic, as they rise and fall in slow motion. Sometimes the magnetic fields become so tangled and stressed that they snap, releasing enormous amounts of energy in events called solar flares and coronal mass ejections, sending billions of tons of plasma hurtling into space at millions of miles per hour. But even these dramatic events, viewed from a distance, seem strangely peaceful, just another expression of the sun's dynamic nature, part of the endless cycle of magnetic activity that has been ongoing since the sun first ignited over 4.5 billion years ago. The sun is not a static object, but a living, changing, evolving entity, and we are privileged to observe it in this moment of cosmic time. A moment that is itself just a heartbeat in the life of a star. As we prepare to move away from the sun and begin our tour of the planets, take one last long look at this magnificent object. Appreciate its constancy, its power held in check by gravity, its generous sharing of energy with all the worlds that circle it. The sun is the reason everything else exists in our solar system, the source of virtually all energy and the anchor of all motion. With that appreciation, we turn and begin our drift outward toward the first of the planets, the small, fast, hot world we call Mercury. Mercury, the silent messenger. The first world we encounter on our journey outward is Mercury, a small rocky sphere that hugs close to the sun, racing around it in just 88 Earth days. Of all the planets, Mercury has the most elliptical orbit, swooping in as close as 29 million miles at its nearest approach and swinging out to 43 million miles at its farthest. This elongated path causes dramatic variations in the intensity of sunlight the planet receives. Though from our quiet perspective in space, Mercury appears serene, a silent witness to the sun's brilliance. Mercury is only slightly larger than our moon, with a diameter of just over 3,000 miles, making it the smallest planet in our solar system. If Earth were the size of a nickel, Mercury would be about the size of a blueberry. Yet despite its small size, Mercury is remarkably dense, the second densest planet after Earth. This density comes from its enormous iron core, which makes up about 85% of the planet's radius, a much larger proportion than any other planet. Scientists believe that early in the solar system's history, a massive collision might have stripped away much of Mercury's outer layers, leaving behind the dense core surrounded by only a thin shell of rock. As we drift closer to Mercury, its surface comes into focus, and what we see is a landscape frozen in time, a cratered wasteland that bears the scars of 4 billion years of asteroid and comet impacts. The surface resembles our moon, pockmarked with craters of every size, from tiny pits just feet across to massive impact basins, hundreds of miles in diameter. The largest of these is Caloris Basin, a vast impact basin nearly 1,000 miles across. Created when an asteroid slammed into Mercury with unimaginable force billions of years ago. The absence of atmosphere means that there's nothing to erode or weather these ancient features. Every impact crater, every ridge, every smooth plain exists just as it did when it formed, a permanent record of Mercury's violent past preserved in airless silence. The largest craters show bright rays of ejecta material spreading across the surface like flower petals. Material that was blasted out during the impact and fell back to create secondary craters and patterns that can extend for hundreds of miles. Mercury's surface is covered with long curved cliffs called scarps, some stretching for hundreds of miles and rising more than a mile high. These formed as the planet's interior cooled and contracted, causing the surface to wrinkle like a drying apple. The largest of these scarps, Discovery Rupiers, stretches for about 400 miles across the surface, a wrinkled testament to the planet's gradual shrinking over billions of years. But perhaps Mercury's most extreme characteristic is its temperature. Being so close to the Sun, the side facing our star can reach blistering temperatures of about 430 degrees Celsius, hot enough to melt lead, zinc, and tin. The rocks themselves glow with heat, and the daytime surface is among the hottest places in the solar system. Yet surprisingly, Mercury is not the hottest planet. That distinction belongs to Venus, whose thick atmosphere traps heat far more effectively than Mercury's airless surface. Because Mercury has essentially no atmosphere to distribute heat, the night side becomes incredibly cold, plummeting to -180 degrees Celsius. This temperature swing of over 600 degrees Celsius is the most extreme in the solar system, a testament to the importance of atmospheres in moderating planetary climates. On Mercury, there's nothing to transport heat from the sunlit side to the dark side, nothing to prevent the rapid escape of heat when a region rotates into darkness. Mercury does have an extremely thin exosphere, barely denser than the vacuum of space itself, with a surface pressure roughly 1/4,000,000th that of Earth's atmosphere. This tenuous envelope consists of atoms that have been blasted off the surface by the solar wind and micrometeorite impacts. It contains mostly oxygen, sodium, hydrogen, helium, and potassium. But these atoms are so sparse and so weakly held by Mercury's modest gravity that they quickly escape into space, requiring constant replenishment from the surface below. Despite the intense heat on Mercury's sunlit surface, scientists have discovered something surprising. Water ice exists in deep craters near the planet's poles. These craters are permanently shadowed, never receiving direct sunlight, and in these dark refuges, temperatures remain cold enough for water ice to survive, perhaps for billions of years. Radar observations and measurements from spacecraft have confirmed the presence of this ice, hidden away in the shadows, a reminder that even on one of the solar system's most extreme worlds, conditions can vary dramatically over short distances. Mercury's day is unusual in a way that would be disorienting if you were standing on its surface. The planet rotates very slowly, taking about 59 Earth days to complete one rotation. Combined with its rapid orbit around the Sun, this creates a situation where one full day-night cycle, one solar day, on Mercury lasts 176 Earth days, twice as long as Mercury's year. This means that if you were standing on Mercury, you would see the Sun rise, slowly climb across the sky for 88 Earth days, then slowly set, followed by 88 days of darkness. Even stranger, due to Mercury's elliptical orbit and its peculiar rotation, an observer in certain locations on the surface would see the Sun rise partway, then reverse and set again before finally rising for good. At sunset, the reverse would happen, with the Sun setting, rising briefly, then setting again. This bizarre celestial dance results from Mercury's orbital dynamics and would make for one of the strangest skies in the solar system. Mercury has no moons, no rings, nothing to accompany it on its swift journey around the Sun. It moves alone, the fastest planet in our solar system, appropriately named after the Roman messenger god known for his speed. In ancient times, Mercury was actually thought to be two different objects because it appears sometimes in the evening sky after sunset and sometimes in the morning sky before sunrise. The Greeks called it Apollo when it appeared in the morning and Hermes in the evening, before realizing it was a single wandering star. From our perspective, floating peacefully above this small, battered world, Mercury appears serene despite its extreme conditions. The ancient craters speak of a time early in the solar system's history, when asteroid impacts were far more common, when the debris left over from planetary formation was still being swept up by the gravity of newly formed worlds. Mercury has collected these scars and preserved them, a memorial to that violent era now long past. The planet's core remains partially molten even after billions of years, generating a weak but measurable magnetic field. This field is only about 1% as strong as Earth's, but is significant because Mercury is the only other rocky planet in the inner solar system besides Earth that generates its own global magnetic field. This field interacts with the solar wind flowing past Mercury, creating a small magnetosphere that provides some protection from the Sun's charged particles, though nothing like the robust protection Earth's magnetic field provides. As we prepare to leave Mercury and continue outward, we can appreciate this little world for what it represents: resilience and endurance. Despite being closest to the Sun, despite enduring temperature extremes that would destroy most materials, despite being bombarded for billions of years by solar radiation and impacts, Mercury endures. It continues its swift orbit, unchanged and unchanging, a permanent fixture in the inner solar system, a world of ancient silence and patient waiting. With this appreciation, we drift onward toward the next world, the mysterious and cloud-shrouded Venus. Venus, the veiled world. As we move outward from Mercury, we approach a world that appears deceptively beautiful from space, its surface hidden beneath a thick blanket of golden clouds that reflect sunlight with brilliant intensity. Venus, the second planet from the Sun, is the brightest natural object in Earth's sky after the Sun and Moon, often called the evening star or morning star depending on where it appears relative to the Sun. Ancient cultures gave Venus special significance, associating it with love and beauty, naming it after the Roman goddess Venus. From our peaceful vantage point in space, Venus appears as a near-perfect sphere wrapped in smooth, featureless clouds that glow with a soft golden hue. These clouds are not water vapor like Earth's clouds, but droplets of concentrated sulfuric acid floating in a carbon dioxide atmosphere so thick that it creates pressure at the surface 92 times greater than Earth's sea level pressure. Standing on Venus's surface would feel like being 3,000 feet underwater. In Earth's oceans, a crushing weight that would instantly destroy any unprotected human. Venus is often called Earth's twin because of their similar sizes, masses, and densities. Venus's diameter is about 12,100 kilometers, just 650 kilometers less than Earth's. Its mass is about 81.5% of Earth's mass, and its density is nearly identical. The two planets likely formed from similar materials in the same region of the early solar system, coalescing from the disk of gas and dust that surrounded the young Sun 4.6 billion years ago. But while Venus and Earth may be twins in size, their evolution has taken dramatically different paths. Venus has become a hellish world with surface temperatures around 467 degrees Celsius, hot enough to melt lead. This extreme heat is caused by a runaway greenhouse effect, one of the most dramatic examples of climate change in our solar system. Venus's thick atmosphere, composed of 96% carbon dioxide, traps incoming solar radiation with devastating efficiency. Here's how the runaway greenhouse effect works on Venus. When sunlight penetrates the clouds and reaches the surface, it warms the rocks and terrain. These heated surfaces then radiate energy back outward, but instead of the visible light that came in, they radiate in the infrared spectrum heat radiation that cannot easily pass through the carbon dioxide atmosphere. The carbon dioxide and the thick cloud layers trap this infrared radiation, preventing it from escaping back into space. This trapped heat warms the atmosphere, which causes more carbon dioxide to be released from surface rocks, which strengthens the greenhouse effect further, creating a self-reinforcing cycle that has pushed Venus's surface temperature to its current extreme level. Remarkably, despite being farther from the Sun, Venus is hotter than Mercury because Venus has an atmosphere that traps heat, while Mercury does not. Venus demonstrates the powerful effect that atmospheres can have on planetary temperatures, a lesson that has profound implications for our understanding of climate on Earth and other worlds. The clouds of Venus are found at altitudes between 40 and 60 kilometers above the surface, creating a main deck about 20 kilometers thick. These clouds are made primarily of sulfuric acid droplets with smaller amounts of water and various sulfur compounds. Above and below this main cloud deck are thinner hazes that extend down to about 32 kilometers and up to about 90 kilometers altitude. The upper haze near the poles is somewhat thicker than elsewhere, creating subtle variations in the planet's appearance. One of Venus's most remarkable features is its atmospheric superrotation. Although the planet itself rotates extremely slowly, taking 243 Earth days to complete one rotation, the atmosphere races around the planet much faster, completing a full circuit in just 4 days. Winds at the cloud tops reach speeds of about 360 kilometers per hour, 60 times faster than the planet's rotation. This creates a situation where the clouds circle Venus in the time it takes the Sun to cross about 1/16 of the way across the sky. The cause of this atmospheric superrotation remains one of the mysteries of planetary science. Scientists have proposed various mechanisms involving solar heating, atmospheric tides, and the exchange of angular momentum between different atmospheric layers, but no single explanation fully accounts for the observed wind patterns. It's one of those phenomena that reminds us how much we still have to learn about how planets and their atmospheres behave. Venus rotates in the opposite direction from most planets in the solar system, a motion called retrograde rotation. While most planets rotate counterclockwise when viewed from above their north poles, Venus rotates clockwise. This means that if you could see through the clouds, you would watch the sun rise in the west and set in the east. The opposite of the motion we see on Earth. The reason for this backward rotation is uncertain, but scientists speculate that a massive collision early in Venus's history might have knocked the planet onto its side, or perhaps even completely flipped it over. The combination of Venus's slow rotation and its retrograde spin creates some interesting effects. A day on Venus, measured from sunrise to sunrise, lasts about 117 Earth days. This means that a Venusian day is shorter than a Venusian year, which lasts 225 Earth days. During one Venusian day, the sun would slowly traverse the sky from west to east, taking weeks to move from horizon to horizon, though in reality the sun would never be visible from the surface due to the thick cloud cover. Beneath those impenetrable clouds lies a surface that has been revealed through radar mapping by spacecraft including NASA's Magellan mission. These radar images show a world dominated by volcanic features, with vast plains of hardened lava covering most of the surface, dotted with thousands of volcanoes ranging from small shield volcanoes to massive peaks taller than Mount Everest. The largest volcanic feature is Mart Mons, rising about 5 miles above the surrounding plains, though this is still lower than Olympus Mons on Mars. Venus's surface also features strange terrain called tesserae, highly deformed regions with complex patterns of ridges and troughs that suggest the surface has been fractured and folded by intense geological forces. These regions are among Venus's most mysterious features, their formation not fully understood, though scientists believe they may represent some of the oldest terrain on the planet's surface. Impact craters on Venus are relatively rare and evenly distributed across the surface, suggesting that the entire surface is relatively young, perhaps only 500 to 750 million years old. It's possible that Venus undergoes periodic episodes of global volcanic resurfacing, events where much of the surface is covered in fresh lava, erasing older features and resetting the geological clock. This would explain why we see so few impact craters compared to Mars or Mercury, and why those craters that do exist appear so well preserved. Above the scorching surface, at altitudes around 50 kilometers, conditions become much more Earth-like. Here, temperatures range between 30 and 70 degrees Celsius, and atmospheric pressure is comparable to Earth's surface. This region has been proposed as a potential target for future exploration, with floating platforms that could drift through the clouds, conducting scientific research in relatively benign conditions compared to the hellish surface below. Some scientists have even speculated that if life exists on Venus, it might be found in these cloud layers, where temperatures and pressures are suitable for liquid water droplets. though the acidic nature of the clouds makes this a challenging environment for any form of life we can imagine. Venus has no moons and no magnetic field, though it does have an induced magnetic field created by the interaction between the solar wind and its ionosphere. Without a global magnetic field, Venus's upper atmosphere is directly exposed to the solar wind, which slowly strips away atmospheric particles over time. Despite this loss, Venus's atmosphere remains incredibly thick, sustained by volcanic outgassing and the release of gases from surface rocks. From our peaceful observation point, Venus appears tranquil, its golden clouds swirling slowly in mesmerizing patterns, hiding the extreme conditions beneath. There's a strange beauty in its appearance, a serenity that masks the reality of its surface environment. Venus reminds us that appearances can be deceiving, that beauty can hide danger, and that planets which seem similar can evolve in radically different directions based on slight differences in their starting conditions and orbital positions. As we prepare to leave Venus and continue our outward journey, we carry with us an appreciation for this mysterious world. Venus shows us the power of greenhouse gases, the importance of planetary atmospheres, and the narrow range of conditions necessary for a planet to remain habitable. It serves as both a warning and a scientific treasure, a laboratory for understanding atmospheric physics and climate processes. With these thoughts, we drift onward toward a blue marble in the darkness, the one place in the universe we know for certain harbors life. Earth and the Moon, our home. Continuing outward from the Sun, we approach the third planet, and suddenly everything changes. Where Mercury was grey and cratered, where Venus was shrouded in golden clouds, here we find a world painted in vivid blues and greens, and whites, a sphere of such striking beauty that it stands out among all the planets like a jewel in the darkness. This is Earth, our home. The only world in the universe we know for certain harbors life. From our vantage point in space, Earth appears as a study in constant motion and vibrant color. Vast oceans cover more than 70% of the surface, their deep blue waters reflecting sunlight in ever-changing patterns. White clouds drift across the face of the planet, forming spirals and bands and clusters, driven by weather systems that circle the globe. Between the blues of the oceans and the whites of the clouds, we see the browns and greens of the continents. Land masses that support nearly 8 billion human beings along with countless other forms of life. Earth is the largest of the rocky planets in the inner solar system, with a diameter of just under 13,000 kilometers at the equator. Its size is part of what makes it habitable, large enough to hold on to a substantial atmosphere through gravity, yet small enough that its interior remains geologically active, with plate tectonics that recycle carbon and regulate long-term climate. This geological activity has helped maintain Earth's habitability for over 3 billion years, far longer than would be possible on a geologically dead world. The most remarkable thing about Earth, the feature that makes it unique among the planets we know, is the presence of liquid water on its surface. Water exists in all three phases on Earth: solid ice at the poles and high mountains, liquid water in the oceans and rivers and lakes, and water vapor in the atmosphere. This water is essential for all life as we know it, serving as a solvent for biochemical reactions, a temperature regulator, and a medium for transport of nutrients and waste. Earth's atmosphere is another key to its habitability, a thin shell of gases that extends from the surface up to about 100 kilometers altitude. though most of the mass is concentrated in the lowest 10 kilometers. His atmosphere is 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. The oxygen is particularly significant because it's maintained by life itself, produced by photosynthetic organisms like plants and algae. Without life constantly replenishing it, Earth's oxygen would gradually be consumed by chemical reactions with rocks and other materials. The atmosphere serves multiple critical functions. It protects the surface from harmful ultraviolet radiation through its ozone layer. A concentration of oxygen molecules at altitudes between 15 and 30 kilometers that absorbs most incoming UV light. It distributes heat around the planet through weather systems, preventing the extreme temperature differences that we see on Mercury and other airless worlds. It provides pressure that allows liquid water to exist at the surface, and it creates weather patterns that distribute rainfall, supporting life across the continents. Earth's magnetic field is another crucial protective feature, generated by the motion of molten iron in the planet's outer core. This field extends far out into space, creating a magnetosphere that shields the planet from the solar wind and cosmic rays. When charged particles from the Sun interact with Earth's magnetic field, they're channeled toward the poles, where they collide with atmospheric molecules and create the beautiful light displays known as auroras. Without this magnetic protection, the solar wind would gradually strip away Earth's atmosphere, as has happened on Mars. The planet's geology is dynamic and constantly changing, driven by heat from the interior that causes convection in the mantle. This heat flow powers plate tectonics, the motion of large segments of crust across the planet's surface. Plates collide to form mountains, separate to create ocean basins, and slide past each other to generate earthquakes. Volcanoes erupt where molten rock finds paths to the surface, adding gases to the atmosphere and creating new land. This geological activity has helped maintain Earth's habitability by recycling carbon between the atmosphere, oceans, and rocks, preventing either a runaway greenhouse effect or a frozen state. But Earth does not orbit alone. Accompanying it on its journey around the Sun is the Moon, Earth's only natural satellite and our constant companion in the cosmic void. The Moon orbits Earth at an average distance of about 384,000 kilometers, close enough that it appears as the second brightest object in our sky, yet far enough that its gravitational influence on Earth remains subtle. The Moon is quite large relative to its parent planet, with a diameter about 1/4 that of Earth. This makes the Earth-Moon system sometimes described as a double planet rather than a planet with a satellite. The Moon's origin is believed to be the result of a massive collision early in Earth's history, when a Mars-sized object struck the young Earth with such force that it ejected enormous amounts of material into orbit. This material gradually coalesced to form the Moon, which has been orbiting Earth ever since. From our position in space, the Moon appears as a grey sphere, its surface covered with craters and vast smooth plains known as maria, which are ancient lava flows that filled large impact basins billions of years ago. Unlike Earth, the Moon has no atmosphere, no weather, and no liquid water on its surface. Its landscape is frozen in time, preserving a record of the intense bombardment that all inner planets experienced during the solar system's youth. The Moon's surface is marked by dramatic contrasts between its bright highlands, heavily cratered ancient terrain, and its dark maria, younger plains of hardened lava. The largest craters show brilliant ray patterns spreading across the surface, ejecta from impacts that were blasted hundreds or even thousands of kilometers from the impact site. Some of these rays are so prominent they can be seen from Earth with the naked eye, giving the Moon its characteristic splotchy appearance. The Moon's gravitational pull on Earth creates tides in our oceans, raising and lowering the sea level twice each day as different parts of the planet rotate through the bulges created by lunar gravity. These tides have shaped coastal ecosystems and may have played a role in the evolution of life as organisms adapted to the rhythmic flooding and exposure of tidal zones. The Moon also helps stabilize Earth's axial tilt, which in turn stabilizes our climate and seasons. Without the Moon, Earth's axis would wobble chaotically over time, causing dramatic climate swings that could make complex life much more difficult. The Moon always shows the same face to Earth, a phenomenon called tidal locking that occurs because the Moon's rotation period exactly matches its orbital period around Earth. This synchronous rotation developed over millions of years as tidal forces from Earth gradually slowed the Moon's rotation until one face permanently faced Earth. The far side of the Moon, sometimes incorrectly called the dark side, remains hidden from Earth but receives just as much sunlight as the near side over the course of a lunar day. Currently, the Moon is gradually moving away from Earth at a rate of about 3.8 centimeters per year, a consequence of tidal interactions between the two bodies. As the Moon recedes, it transfers angular momentum to Earth's rotation, causing our planet's rotation to slow very gradually. Billions of years ago, the Moon was much closer to Earth and appeared much larger in the sky, while days on Earth were significantly shorter. Billions of years in the future, if the Earth-Moon system survives that long, the Moon will be much farther away, appearing smaller in our sky, and Earth's day will be considerably longer than the 24 hours we currently experience. From our peaceful vantage point, we can observe the Earth-Moon system as a whole, watching how they orbit their common center of mass, which lies about 4,700 kilometers from Earth's center, well within Earth's mantle. This orbital dance has continued for over 4 billion years, with the Moon faithfully accompanying Earth on its journey around the Sun, a silent guardian and companion in the cosmic darkness. Earth's orbit around the Sun is nearly circular, maintaining an average distance of about 150 million kilometers. This distance, called 1 astronomical unit, is used as a standard for measuring distances in the solar system. Earth completes one orbit in 365.25 days, which is why we need leap years to keep our calendar synchronized with the seasons. The planet's axis is tilted about 23.4 degrees relative to its orbital plane, creating the seasons as different hemispheres tilt toward or away from the Sun during the year. As we prepare to leave Earth and the Moon and continue our outward journey, we carry with us a renewed appreciation for this remarkable world. Earth is not just our home, but a unique experiment in habitability, a world where countless factors have aligned to create and sustain the conditions for life. The presence of liquid water, a protective atmosphere and magnetic field, the right distance from the Sun, a large Moon to stabilize our climate, active geology to recycle elements. These are all pieces of the puzzle that make Earth the paradise it is. With gratitude for this cosmic gift, we drift onward toward the next world, the red desert planet we call Mars. Mars, the red stillness. Farther out, Mars presents itself, a cold and distant world painted in deep reds and oranges. This is the red planet, named for the Roman god of war, a cold desert world that represents the edge of the inner solar system. Mars appears as a reddish-orange sphere in the darkness, smaller than Earth but clearly visible even from great distances thanks to its characteristic color. Mars is about half the size of Earth, with a diameter of about 6,800 kilometers. Despite being significantly smaller than Earth, Mars has a similar total land area because it lacks Earth's vast oceans. If we could drain Earth's oceans and compare just the land surfaces, Mars would offer a comparable amount of territory for exploration. This similarity in land area, combined with evidence of past water and a day length very close to Earth's, has made Mars the most studied planet in our solar system, besides Earth itself. The red color that gives Mars its nickname comes from iron oxide common rust that coats much of the planet's surface. When Mars formed, it contained significant amounts of iron, and over billions of years this iron has oxidized, literally rusted, giving the rocks and dust their characteristic color. This dust is incredibly fine, and Mars's thin atmosphere can lift it high into the sky, sometimes creating global dust storms that obscure the entire planet for months at a time. These dust storms give Mars's sky its distinctive salmon pink color, quite different from Earth's familiar blue. Mars's atmosphere is extremely thin, with a surface pressure less than 1% of Earth's sea level pressure. This wispy atmosphere is composed of 95% carbon dioxide, with small amounts of nitrogen and argon. Because the atmosphere is so thin, it provides little greenhouse warming, and Mars's surface temperature averages about -63 degrees Celsius. On a warm summer day near the equator, temperatures might reach 17 degrees Celsius. Comfortable for humans, but at night those same equatorial regions plunge to -73 degrees Celsius, cold enough to freeze carbon dioxide out of the atmosphere. The thin atmosphere also means that Mars's surface is exposed to much more radiation from space than Earth's surface. Without a thick atmosphere and without a global magnetic field to deflect charged particles, Mars receives far more cosmic rays and solar radiation than Earth. This high radiation environment would be hazardous for any life on the surface and represents one of the major challenges for human exploration of the planet. Despite its cold, dry, present-day conditions, Mars clearly had a very different past. As we drift over the surface, we can see features that could only have been carved by flowing water. Ancient river valleys that wind across the landscape like Earth's rivers. Deltas where rivers once emptied into lakes or seas, and vast outflow channels that suggest massive floods occurred billions of years ago. The presence of these features tells us that Mars must once have had a much thicker atmosphere and much warmer temperatures, conditions that allowed liquid water to flow across its surface. Where did all that water go? Much of it is still on Mars, locked away as ice beneath the surface, especially in the polar regions. Mars has prominent ice caps at both poles that grow and shrink with the seasons. These caps contain both water ice and dry ice-frozen carbon dioxide, with the seasonal changes driven by the freezing and sublimation of carbon dioxide. Recent discoveries have also found evidence of liquid water that flows seasonally in some locations, appearing as dark streaks on crater walls and steep slopes during warm periods. Though these flows are extremely briny and would freeze or evaporate quickly if exposed to the surface conditions. The loss of Mars's atmosphere is thought to be connected to the planet's small size and lack of a global magnetic field. Mars's core is smaller relative to the planet's size than Earth's core, and at some point in Mars's past, the core cooled enough that it stopped generating a magnetic field. Without magnetic protection, The solar wind began slowly stripping away the atmosphere, a process that has continued for billions of years. The solar wind collides directly with Mars's upper atmosphere, giving atoms enough energy to escape the planet's gravity. Mars's surface is divided into two dramatically different hemispheres. The southern hemisphere is ancient and heavily cratered, similar to the lunar highlands, representing terrain that has remained largely unchanged for over 3 billion years. The northern hemisphere is younger and smoother, lying about 3 kilometers lower in elevation than the south, forming vast plains that some scientists believe may once have been the bed of an ancient ocean. The boundary between these two hemispheres is one of the most dramatic features on any planet. One of Mars's most impressive features is Olympus Mons, the largest volcano in the solar system. This massive shield volcano rises about 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest, and stretches about 600 kilometers across its base. If you were standing in the middle of Olympus Mons, you wouldn't be able to see its edges because they would be beyond the horizon, and the slopes are so gentle that you might not even realize you were climbing a mountain. Nearby, a chain of 3 other giant volcanoes forms the Tharsis Montes, a volcanic region that dominates Mars's western hemisphere. These volcanoes are inactive today, but they must have been spectacularly active in Mars's past, erupting for millions or even billions of years to build up their enormous bulk. The heat from these volcanic regions may have played a role in maintaining warmer conditions on early Mars, releasing gases into the atmosphere and providing energy that could have supported microbial life. On the opposite side of the planet from Tharsis lies Valles Marineris, a vast canyon system that dwarfs Earth's Grand Canyon. This system of interconnected canyons stretches about 4,000 kilometers across the Martian surface, over 1/5 of the way around the planet. In places, the canyons are up to 7 kilometers deep and 200 kilometers wide. From orbit, Valles Marineris appears as a massive scar across Mars's facer feature, so large it would stretch from New York to Los Angeles if placed on Earth. Mars has 2 small moons, Phobos and Deimos, both named after the sons of the Roman war god Mars. These moons are tiny compared to Earth's moon, more like captured asteroids than traditional satellites. Phobos, the larger and inner moon, is only about 22 kilometers across at its widest, heavily cratered and covered with deep grooves that may be stress fractures caused by tidal forces from Mars. Phobos orbits incredibly close to Mars, just 6,000 kilometers above the surface, so close that it completes 3 orbits every Martian day. Deimos, the outer moon, is even smaller, about 12 kilometers across, and orbits at a more sedate pace, completing 1 orbit every 30 hours. Both moons are probably captured asteroids, objects that originally formed in the asteroid belt between Mars and Jupiter, but were somehow captured by Mars's gravity early in the solar system's history. They're among the darkest objects in the solar system, reflecting only about 6% of the sunlight that hits them. From the surface of Mars, Phobos would appear as a small but clearly visible object racing across the sky, rising in the west and setting in the east due to its rapid orbit. It would pass through all its phases, from full to new and back again, in just 11 hours. Deimos would appear much like a bright star, taking about 2.5 days to cross the sky. Mars has been the target of more exploration missions than any planet besides Earth. Dozens of spacecraft have been sent to Mars with varying degrees of success. Currently, several orbiters circle Mars, studying its atmosphere and surface. while rovers like Perseverance and Curiosity crawl across the surface, analyzing rocks and searching for signs of past life. These missions have revealed that Mars was once much more habitable than it is today. We now know that liquid water flowed across the surface for hundreds of millions or possibly billions of years. We've found minerals that form only in the presence of water clays and sulfates that indicate prolonged exposure to liquid water. We've found organic molecules, carbon-based compounds that on Earth are associated with life, though on Mars they could have formed through non-biological processes. The question of whether life ever arose on Mars remains unanswered, but the evidence increasingly suggests that early Mars had all the ingredients necessary: liquid water, energy sources, and organic chemistry. If life did arise on Mars, it was almost certainly microbial, and if any Martian life still exists, it's probably hiding deep underground where liquid water might still exist and where radiation from space cannot penetrate. As we prepare to leave Mars and continue our journey outward, we carry with us a sense of what might have been. Mars shows us that planetary environments can change dramatically over time, that a world which once had rivers and possibly oceans can become a cold desert. It reminds us how fragile planetary habitability can be, how critical factors like magnetic fields and atmosphere retention are for maintaining hospitable conditions. But Mars also inspires us with its mysteries, challenging us to explore, to learn, to understand. With this inspiration, we drift onward, leaving the red planet behind as we head toward a region filled with millions of rocky fragments. The asteroid belt. Cosmic fragments. Between the orbit of Mars and the giant planet Jupiter lies a vast region of space populated by millions of rocky fragments, remnants from the early solar system that never coalesced into a planet. This is the asteroid belt, a ring of debris that circles the Sun between about 2 and 3.5 astronomical units from our star. From our peaceful vantage point, we enter this region and find it far more spacious than popular culture often suggests. Despite containing millions of asteroids, the belt is mostly empty space, with the average distance between asteroids measured in hundreds of thousands of kilometers. The asteroids in this belt range dramatically in size. The largest, Ceres, is about 940 kilometers in diameter and contains roughly 1/3 of the total mass of all asteroids combined. Ceres is large enough and round enough to be classified as a dwarf planet, the only one in the inner solar system. Most asteroids are much smaller, ranging from boulders a few meters across to chunks hundreds of kilometers in diameter. Scientists estimate there are about 2 million asteroids larger than 1 kilometer. These asteroids are not uniformly distributed throughout the belt. Instead, they're organized into various families and groups, collections of asteroids that share similar orbits and compositions, suggesting they may be fragments of larger parent bodies that were broken apart by collisions. Some regions of the belt are more densely populated than others, while certain orbital regions are nearly empty, cleared out by gravitational resonances with Jupiter that make those orbits unstable over long time scales. The asteroids themselves are fragments of the planet that never was. Solar system's history, the material in this region was prevented from accreting into a planet by Jupiter's powerful gravity. Jupiter's influence stirred up the orbits of the planetesimals in this region, causing them to collide at high speeds that shattered them, rather than allowing them to stick together and grow. Over billions of years, these repeated collisions have ground down the original population of large objects, creating the diverse collection of sizes we see today. As we drift through the belt, we can observe asteroids up close, seeing their diverse shapes and compositions. Most asteroids are irregularly shaped, tumbling slowly as they orbit the Sun. Their surface is covered with craters from billions of years of impacts. Some are solid pieces of rock or metal, while others are rubble piles, collections of smaller fragments held together by their own weak gravity. So loosely bound that a person could potentially jump off their surface and escape their gravitational pull. Asteroids are classified into different types based on their composition and the way they reflect sunlight. C-type asteroids are the most common, making up about 75% of known asteroids. These are carbonaceous asteroids, dark objects rich in carbon and water-bearing minerals, primitive remnants from the outer solar system that have changed little since the solar system formed. Cis-type asteroids are the second most common type, composed mainly of silicate rocks and metals, representing material from the inner solar system. Mean-type asteroids are relatively rare, composed mostly of metallic iron and nickel, possibly the exposed cores of larger asteroids that were shattered by impacts. The motion of asteroids through the belt is surprisingly orderly despite the millions of objects involved. Each asteroid follows its own elliptical orbit around the Sun, determined by its orbital parameters established billions of years ago. These orbits can be quite elongated, carrying some asteroids close to the Sun and others farther out beyond Jupiter's orbit. Collisions, while they do occur, are relatively rare on human timescales, though over millions of years they continue to reshape and fragment the asteroid population. Some asteroids have been visited by spacecraft, allowing us to observe them in stunning detail. NASA's Dawn mission orbited both Vesta and Ceres, revealing worlds more complex and diverse than expected. Vesta, the second largest asteroid, has a surface scarred by ancient volcanic activity and a massive impact crater near its south pole that nearly shattered the entire asteroid. Ceres has a thin atmosphere, bright spots that may be deposits of salt or ice, and evidence of a subsurface ocean that may still exist in some form. As we observe the asteroids drifting peacefully through the darkness, we can appreciate them for what they represent: time capsules from the early solar system, fragments of the material that formed the planets, survivors of 4.5 billion years of cosmic history. They're reminders that planet formation is a violent, chaotic process, that not all material manages to accrete into planets, and that the solar system's history includes countless collisions and near misses. The asteroid belt also represents potential resources for future space exploration. These objects contain metals, water, and other materials that could be valuable for spacecraft construction or life support. Some asteroids are essentially flying mountains of metal, with more platinum group metals than have ever been mined on Earth. Others contain water ice that could be used for rocket fuel or life support in space. Not all asteroids remain in the belt. Gravitational perturbations from Jupiter and other planets occasionally send asteroids onto new orbits that can bring them into the inner solar system. These near-Earth asteroids sometimes come close to our planet, and very rarely they impact Earth. While large impacts are extremely rare on human timescales, they have played an important role in Earth's history. As we prepare to leave the asteroid belt and continue our journey outward, we carry with us an appreciation for these small worlds. They may be fragments, failed planets, remnants of destruction, but they're also survivors, witnesses to the entire history of the solar system and potential keys to understanding how planets form and evolve. With this appreciation, we drift onward, leaving the realm of rocky worlds behind as we approach the domain of the giants, where massive planets made of gas and ice reign supreme. The first of these giants, Jupiter already looms large ahead of us, the king of planets waiting in the darkness. Jupiter, the majestic giant. As we move beyond the asteroid belt, the character of our journey changes dramatically. Here, in the outer solar system, the planets are no longer small rocky worlds but massive spheres of gas and liquid. Planets so large that they dwarf the terrestrial worlds we visited. The first and largest of these giants is Jupiter, a planet so immense that it contains more than twice the mass of all other planets in the solar system combined. From our peaceful vantage point in space, Jupiter appears as a colossal presence, its distinctive bands of clouds visible even from great distances. Jupiter orbits the Sun at an average distance of about 778 million kilometers, over 5 times farther from the Sun than Earth. Even at this great distance, Jupiter receives enough sunlight to illuminate its clouds brilliantly, and internal heat from the planet's core adds to the energy that drives its atmospheric dynamics. Jupiter is the fastest spinning planet in our solar system, completing one rotation in just under 10 hours, which causes it to bulge noticeably at the equator. The planet's diameter at the equator is about 143,000 kilometers, 11 times Earth's diameter. This enormous size means that Jupiter's volume is large enough to contain over 1,300 Earths. Yet despite this huge volume, Jupiter's mass is only about 318 times Earth's mass, reflecting the planet's composition of lightweight hydrogen and helium rather than dense rock and metal. As we drift closer to Jupiter, the details of its atmosphere come into focus. The planet's surface is not solid, but rather a gradual transition from gas to liquid as we descend into the depths. What we see as the surface is actually the top of a vast ocean of clouds, organized into distinctive bands that circle the planet parallel to the equator. These bands are created by powerful winds and jet streams that blow at different altitudes and latitudes, with wind speeds reaching up to 640 kilometers per hour in some regions. The lighter colored bands, called zones, are regions where gas rises from the planet's interior, carrying heat upward. The darker bands, called belts, are regions where cooler gas descends back into the depths. The boundaries between zones and belts are marked by powerful jet streams, rivers of wind that can persist for decades or even centuries. The colors we see in these bands come from trace chemicals in the atmosphere, compounds of sulfur and phosphorus that create yellows, browns, whites, and reds against the planet's otherwise bland hydrogen atmosphere. Jupiter's most famous feature is the Great Red Spot, a massive storm system that has been raging for at least 300 years, and possibly much longer. This anticlonic storm, a high-pressure system that rotates counterclockwise in Jupiter's southern hemisphere, is large enough to swallow 2 or 3 Earths. The storm's distinctive red color comes from complex chemical reactions involving sulfur compounds and organic molecules, though the exact chemistry remains uncertain. The Great Red Spot is not Jupiter's only storm. All across the planet's atmosphere we can see smaller white and brown ovals, smaller storm systems that can last for decades. Jupiter's atmosphere is in constant turbulent motion, with storms forming and dissipating, merging and splitting, creating an ever-changing face. Lightning flashes in Jupiter's clouds are more powerful than any lightning on Earth, and the planet experiences aurorae at its poles that dwarf Earth's northern and southern lights. Beneath the visible cloud tops lies one of the most extreme environments in the solar system. As we descend into Jupiter's atmosphere, pressure and temperature increase steadily. About 1,000 kilometers down, the pressure becomes so great that hydrogen is compressed into a metallic liquid state, a material that only exists under extreme conditions. This metallic hydrogen layer extends for thousands of kilometers deep into Jupiter's interior and is responsible for the planet's powerful magnetic field. Jupiter's magnetic field is the strongest of any planet in the solar system, about 14 times stronger than Earth's at Jupiter's cloud tops. This field extends millions of kilometers out into space, creating a magnetosphere so large that if we could see it from Earth, it would appear several times larger than the full moon in our sky. The magnetosphere traps charged particles from the solar wind, creating intense radiation belts that would be lethal to unshielded humans. Jupiter is not alone in its orbit. The planet is accompanied by at least 97 known moons, from tiny irregular captured asteroids just a few kilometers across to massive worlds larger than the planet Mercury. The 4 largest moons, discovered by Galileo Galilei in 1610, are worlds of remarkable diversity and scientific interest. These Galilean satellites orbit Jupiter in neat circular paths, visible even through small telescopes from Earth. Io, the innermost of the large moons, is the most volcanically active body in the solar system. Its surface is constantly being resurfaced by eruptions of molten rock, with hundreds of active volcanoes spotted across the moon's tortured landscape. This volcanic activity is driven by tidal heating, the gravitational tug-of-war between Jupiter and the other Galilean moons that flexes Io's interior and keeps it molten. Europa, the second Galilean moon, is covered by a shell of water ice that may hide one of the most promising locations to search for life in our solar system. Beneath that ice lies a global ocean of liquid water, kept liquid by tidal heating. This subsurface ocean may be in contact with a rocky sea floor, creating conditions potentially suitable for life. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury and is the only moon known to generate its own magnetic field. Callisto, the outermost Galilean moon, is heavily cratered and appears geologically dead, its ancient surface bearing the scars of 4 billion years of impacts. As we observe Jupiter from our peaceful position in space, we can appreciate its role as the solar system's protector. Jupiter's immense gravity has shaped the architecture of the entire solar system, clearing out the asteroid belt and deflecting or capturing countless comets and asteroids that might otherwise have struck the inner planets. Some scientists believe that Earth's ability to sustain life for billions of years may owe something to Jupiter, which has reduced the impact rate on our planet. With this appreciation, we drift onward toward the next giant, a world famous for its stunning rings, Saturn. Saturn, ring splendor. Continuing outward from Jupiter, we encounter another gas giant, though one with a character distinctly different from the king of planets. Saturn orbits the Sun at an average distance of about 1.4 billion kilometers, nearly twice as far as Jupiter, in a realm where sunlight is dim and temperatures are frigid. Yet even from this great distance, Saturn catches what little sunlight reaches it and reflects it back with a beauty that has made it one of the most recognizable objects in our solar system. This is Saturn, the ringed wonder, a planet whose stunning ring system makes it instantly identifiable. Saturn is the second largest planet in our solar system, with an equatorial diameter of about 120,000 kilometers, about 9 times Earth's diameter. Like Jupiter, Saturn rotates rapidly, completing one rotation in just over 10.5 hours, which creates a pronounced equatorial bulge. What makes Saturn unique among the planets is its magnificent system of rings. From our peaceful vantage point in space, we can see these rings in their full glory, extending outward from the planet in a vast, flat disk that spans more than 280,000 kilometers from edge to edge, yet is incredibly thin in most places, no more than 10 meters thick. The rings are not solid, but are composed of countless individual particles ranging in size from dust grains to house-sized boulders, each particle orbiting Saturn independently. Most of these particles are made of water ice, some pure and white, others contaminated with dust and organic compounds that give them colors ranging from white to pink to brown. From a distance, the rings appear to be continuous sheets, but as we move closer, we can see that they're actually divided into distinct bands separated by gaps. The most prominent gap is the Cassini division, a space about 4,700 kilometers wide that separates the bright B ring from the outer A ring. The rings show incredible structure at all scales. There are thousands of ringlets and gaps, some created by resonances with Saturn's moons, others by small moonlets embedded within the rings themselves. Some regions of the rings are smooth and uniform, while others show complex braided patterns, kinks, and clumps that shift and change over time. Saturn itself, beneath the rings, is a world of swirling clouds and powerful winds, though less dramatically colorful than Jupiter. The planet's atmosphere is composed primarily of hydrogen and helium, with traces of methane, ammonia, and water vapor. The clouds form bands similar to Jupiter's, though more subtle, with wind speeds reaching up to 1,800 kilometers per hour near the equator, the fastest winds in the solar system. At Saturn's North Pole lies one of the solar system's most bizarre features, a hexagonal jet stream that creates a perfect six-sided pattern in the clouds. This hexagon is enormous, with sides longer than Earth's diameter, and it rotates at the same rate as Saturn's interior. Saturn has at least 146 known moons, ranging from tiny moonlets just a few kilometers across to Titan, the second largest moon in the solar system. Titan is a world of remarkable interest, the only moon in the solar system with a thick atmosphere, a nitrogen-rich envelope denser than Earth's atmosphere that completely obscures the surface from visible light. Enceladus, a small moon with a diameter of only about 500 kilometers, has become one of the solar system's most intriguing targets for astrobiology. This little moon has active geysers at its south pole that spew water vapor, ice particles, and organic compounds into space, indicating that Enceladus has a subsurface ocean of liquid water beneath its icy shell. From our peaceful observation point, Saturn appears as an artistic masterpiece, a planet and ring system of such perfect symmetry and beauty that it almost seems designed for visual appeal. The rings catch the light at various angles, sometimes appearing wide open as we see them nearly face on, other times appearing as a thin line when we see them edge on. Saturn reminds us that the universe can create structures of stunning beauty through purely natural processes, that the laws of physics and the random arrangement of matter can produce scenes of such aesthetic perfection that they inspire awe. As we prepare to leave Saturn and continue our journey deeper into the outer solar system, we carry with us the memory of those magnificent rings. With this appreciation, we drift onward toward the next planet, a tilted ice giant that rolls through space in a manner unlike any other world. Uranus, the tilted ice giant. Continuing outward from Saturn's realm, we enter a region of the solar system where sunlight is so dim and temperatures so cold that even giant planets appear different from those closer to the Sun. Here, about 2.9 billion kilometers from the Sun, nearly 20 times farther than Earth's orbit, we encounter Uranus, a planet so unusual in its orientation that it appears to roll through space like a ball rather than spinning like a top. Uranus is the seventh planet from the Sun and the third largest planet in our solar system, with a diameter of about 51,000 kilometers, roughly 4 times Earth's diameter. Despite this substantial size, Uranus is much less massive than Jupiter or Saturn because it's composed of different materials. While Jupiter and Saturn are primarily hydrogen and helium, Uranus is an ice giant composed largely of water, methane, and ammonia ices surrounding a small rocky core. The most striking feature of Uranus is its extreme axial tilt. While most planets have their rotational axes roughly perpendicular to their orbital planes, Uranus is tilted 98 degrees. This means that Uranus rotates nearly on its side, with its poles alternately pointing almost directly at the Sun as it orbits. In practical terms, this creates the most extreme seasons in the solar system. During Iranian summer, one pole points at the Sun and experiences continuous daylight for about 42 Earth years, while the other pole experiences continuous darkness. Then, as Uranus continues in its 84-year orbit, the seasons gradually change, with each pole eventually trading places. From our observation point in space, Uranus appears as a featureless blue-green sphere, its color created by methane in its upper atmosphere. Methane absorbs red light, but reflects blue and green wavelengths, giving Uranus its distinctive cyan appearance. Unlike Jupiter and Saturn, which show dramatic bands and storm systems, Uranus's atmosphere appears remarkably bland when observed in visible light. Uranus's atmosphere is composed of about 83% hydrogen, 15% helium, and 2% methane, with traces of water and ammonia. Unlike Jupiter and Saturn, Uranus radiates very little heat from its interior, only about as much as it receives from the Sun. Uranus has a magnetic field, but it's very unusual. Unlike the magnetic fields of most other planets, which are roughly aligned with their rotational axes, Uranus's magnetic field is tilted 59 degrees relative to its rotational axis and is offset from the planet's center. This creates a highly asymmetric magnetosphere that wobbles dramatically as the planet rotates. Uranus has a faint ring system discovered in 1977. Unlike Saturn's bright, icy rings, Uranus's rings are dark and narrow, composed of material that reflects very little light, probably organic compounds darkened by radiation. The planet has at least 28 known moons, most of them small and irregularly shaped. The 5 largest moons are all icy worlds between about 470 and 1,600 kilometers in diameter. Miranda, the smallest of the large moons, is one of the most geologically diverse bodies in the solar system, despite its small size. From our peaceful vantage point, Uranus appears tranquil, a distant ice giant rolling through space in its unique sideways configuration. The pale blue-green sphere reminds us that the outer solar system is a realm of cold and darkness, where even the giant planets receive so little sunlight that they appear dim compared to the blazing brightness of the inner planets. As we prepare to continue our journey outward toward the last of the major planets, we appreciate Uranus for its uniqueness, its reminder that not all planets follow the same rules. With this appreciation, we drift onward, toward the outermost known major planet, the deep blue world at the edge of the Sun's gravitational dominion. Neptune, the deep blue frontier. In the outer reaches of the Sun's realm, nearly 4.5 billion kilometers from our star, 30 times farther than Earth's orbit, we encounter the last of the major planets, Neptune. This distant ice giant marks the boundary of the Sun's major planetary system, the final large world before we enter the realm of dwarf planets and frozen remnants. From our peaceful position in space, Neptune appears as a striking deep blue sphere, its color more intense than Uranus's pale cyan. Neptune is slightly smaller than Uranus, with a diameter of about 49,000 kilometers, but it's more massive, containing about 17 times Earth's mass. Like Uranus, Neptune is composed primarily of water, methane, and ammonia ices surrounding a rocky core, with an envelope of hydrogen and helium gas above. The deep blue color that distinguishes Neptune from Uranus comes from methane in its atmosphere, the same gas that colors Uranus. However, Neptune's more intense color suggests there must be some additional component that enhances the blue appearance. Despite being farther from the Sun and receiving less energy, Neptune is surprisingly active. Unlike Uranus, which radiates very little internal heat, Neptune radiates about 2.6 times as much energy as it receives from the Sun. This internal heat drives powerful weather systems, making Neptune's atmosphere one of the most dynamic in the solar system. Neptune's winds are the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour in some regions. These supersonic winds blow primarily in the same direction as the planet's rotation near the equator, but in other regions, they blow in complex patterns. The planet's atmosphere shows bright white clouds of methane ice crystals that form at high altitudes and drift with the winds. These clouds cast shadows on the cloud deck below them, creating an ever-changing atmospheric portrait. Neptune has 14 known moons, the largest of which is Triton, one of the most fascinating objects in the solar system. Triton is unusual in several ways. First, it's large, with a diameter of about 2,700 kilometers. Second, it orbits Neptune in a retrograde direction, opposite to the planet's rotation. Third, it's geologically active despite being one of the coldest objects in the solar system, with geysers that erupt nitrogen gas from its icy surface. Triton's retrograde orbit and large size strongly suggests that it didn't form in orbit around Neptune, but was instead captured from the Kuiper belt. The capture of Triton likely had devastating consequences for Neptune's original satellite system. From our peaceful observation point, we can see Neptune as it truly is, a cold, distant world where conditions are almost incomprehensibly extreme, yet a world that remains active and dynamic, driven by internal heat and powerful atmospheric circulation. Neptune represents the edge of the major planetary system, the last of the giants, the final substantial world before the realm of frozen dwarf planets and cometary remnants. As we prepare to leave Neptune and venture into the outermost reaches of the solar system, we carry with us an appreciation for this distant world. Neptune reminds us that even at the edge of the Sun's influence, where light is dim and cold is profound, the laws of physics continue to operate, creating worlds of complexity and beauty. With this appreciation, we drift onward, leaving the major planets behind as we enter the realm of dwarf planets and the distant frozen bodies that mark the true edge of the solar system. Beyond Neptune, the outer reaches and the journey home. As we drift beyond Neptune's orbit, the character of our journey changes once again. Here, In the cold outer reaches of the solar system, we leave behind the realm of major planets and enter a region populated by smaller, frozen worlds, remnants from the solar system's formation, that have remained largely unchanged for 4.5 billion years. This is the Kuiper Belt, a vast region of icy bodies that extends from Neptune's orbit out to about 50 astronomical units from the Sun. The Kuiper Belt contains objects made of frozen volatiles, water ice, methane ice, ammonia ice, and other compounds that would quickly evaporate closer to the Sun but remain stable in the deep freeze of the outer solar system. These objects range in size from small comets just a few kilometers, across to large dwarf planets, hundreds or even thousands of kilometers in diameter. The largest known Kuiper Belt object is Pluto, which orbits the Sun every 248 years. NASA's New Horizons mission revealed Pluto to be a world of surprising geological complexity and beauty when it flew by in July 2015. The surface features mountains of water ice that rise as high as Mount Rainier on Earth and smooth plains of frozen nitrogen. Beyond Pluto lie other large Kuiper Belt objects, and farther still, perhaps beginning at a few thousand astronomical units and extending to as far as 100,000 astronomical units or more, lies the hypothetical Oort cloud, a vast spherical shell of icy bodies that represents the true edge of the Sun's gravitational domain. As we float here in the outer darkness, the Sun has become just a bright star, no longer appearing as a disk but as a point of light. The planets are invisible from this distance, too small and too faint to see. Earth, our home, is completely lost in the glare of the Sun. From this perspective, we can see our solar system in its entirety, a small bubble of activity in the vast emptiness of space. The Sun and its family of planets, moons, asteroids, comets, and dwarf planets occupy a tiny region compared to the distances between stars. As we begin our gentle return, drifting back through the solar system we've just toured, there's no hurry, no need to rush. Space is patient, and so can we be, floating in this cosmic silence, suspended between worlds. From our position in the outer darkness, we can look back at the entire solar system spread out before us, the Sun a brilliant point at the center, the planets arranged in their orbits. This journey has taken us from intense heat to profound cold, from small rocky worlds to gas giants larger than 1,000 Earths, from the familiar blue of our home planet to the alien landscapes of distant moons. We've witnessed the violence preserved in impact craters billions of years old, and we've seen the serene beauty of Saturn's rings catching the light. Each world we've visited tells part of the story of how our solar system formed and evolved. But beyond scientific knowledge, our journey has been about something else. Perspective. From our position floating in space, millions or billions of kilometers from Earth, our planet appears as a tiny speck, barely visible. All of human history, all of our joys and sorrows, all of our conflicts and achievements have occurred on that tiny speck. This perspective is humbling. It reminds us that the things we worry about, the problems that seem so large and urgent, are tiny when measured against the scale of the cosmos. Yet this perspective is also empowering. We are part of this cosmos, made of the same elements as the stars, subject to the same physical laws as the planets. As we continue our drift back toward Earth, we can reflect on our place in this vast system. We're newcomers as a species, existing for less than 1 million years on a planet that's 4.5 billion years old. Yet in this brief moment of cosmic time, we have achieved something remarkable. We've developed the ability to leave our planet, to understand the laws that govern the universe, to appreciate the beauty and complexity of existence. Now, as Earth grows larger again in our view, we can see its blue oceans, its white clouds, its brown continents and green forests. From space, Earth appears peaceful, serene, a jewel in the darkness. As we approach our home world, we carry with us all we've learned and experienced on this peaceful tour. We've seen the diversity of worlds that orbit our sun, each with its own character and story. We've witnessed the power of gravity that holds everything in orbital harmony, the energy of the sun that warms the planets, the endless motion that has continued for billions of years. Most importantly, we've gained perspective on our own world and our place in the universe. Earth is small, yes, fragile even, but it's also precious beyond measure, the only world we know for certain that harbors life, consciousness, meaning. In all the worlds we visited, none can match Earth's delicate balance, its perfect conditions for life. As your consciousness settles gently back into your body, as you feel the familiar weight of gravity once more, you bring with you the peace of the cosmos, the vastness you've witnessed, the silence you've experienced, the beauty you've observed. All of these remain with you, a reminder that beyond the noise and chaos of daily life, there exists a universe of profound tranquility. The planets continue their ancient dance around the sun. The asteroids drift in their patient orbits. The moons circle their parent worlds. All of this cosmic machinery operates with perfect precision, indifferent to our worries, unconcerned with our troubles. And in that indifference, there is peace. The universe simply is, existing in its own eternal present, neither hurrying nor delaying. You can return to this peaceful place whenever you need it. Close your eyes, take a breath, and remember the feeling of floating among the planets, of drifting through the silence between worlds. That peace is always there, waiting for you, as constant as the orbit of the planets, as eternal as the light of the stars. Let your breathing slow now, becoming deeper, more relaxed. Feel the tension draining from your body as you remember the weightlessness of space, the freedom of drifting without constraint. The solar system continues its journey around the galactic center, and you continue your journey through life. But for this moment, there is only stillness, only peace, only the gentle comfort of cosmic perspective. Rest now, knowing that you are part of something vast and beautiful, a universe that has existed for billions of years and will continue for billions more. Your worries are temporary, your troubles fleeting, but the peace of the cosmos is eternal. Float in that peace, rest in that stillness. Let sleep come naturally, gently, like starlight falling softly through the darkness of space. The tour is complete. The journey is done. Now there is only rest, only peace, only the infinite calm of the universe cradling you in its vastness. Drift now, peacefully, into sleep. If you enjoyed this peaceful journey through our solar system, please consider liking this video and subscribing to Behind the Sleep for more relaxing space content. Sweet dreams, space travelers, and may your rest be as peaceful as the cosmic silence we've explored together. Extended Reflections, the Cosmic Perspective. As we float here in the tranquility of space, Having completed our tour of the solar system, let's take a moment to truly absorb what we've witnessed. The journey we've undertaken spans distances that dwarf anything in human experience. From Mercury, just 29 million miles from the Sun at its closest, to Neptune at nearly 3 billion miles away, we've crossed a gulf that light itself takes over 4 hours to traverse. Consider the scale of what we've seen. If we were to model the solar system with the Sun as a basketball, Mercury would be a tiny ball bearing about 25 feet away. Earth would be another ball bearing 92 feet from our basketball sun. Jupiter, despite being the largest planet, would only be about the size of a tennis ball, placed nearly 500 feet away. Neptune, at the edge of the planetary system, would be a marble sitting nearly 3,000 feet distant, and the space between these objects, mostly empty, a vast ocean of nothing peppered with these tiny islands of matter. Yet within this seemingly empty space, within this vast cosmic desert, the forces of gravity weave invisible threads that bind everything together. Every planet feels the pull of every other planet. Every moon tugs gently on its neighbors, and the sun's gravity reaches out to hold even the most distant objects in its embrace. This is the music of the spheres that ancient philosophers imagined, not actual sound. For sound cannot travel through the vacuum of space, but a gravitational harmony, a cosmic symphony played out over billions of years. Think about the age of what we've witnessed. The sun has been shining for 4.5 billion years. Billion, a number so large it becomes almost meaningless. If you could count one number every second, it would take you over 140 years just to count to 4.5 billion once. And the sun has been burning for that many years, steadily converting hydrogen to helium, pouring energy out into space, sustaining the dance of planets around it. The surfaces we've observed preserve history on timescales that dwarf human civilization. Those craters on Mercury and the Moon, many of them formed over 3.5 billion years ago, when Earth was still young and life was just beginning to emerge in our oceans. They've remained unchanged all this time, patient monuments to ancient violence, waiting in airless silence for someone to come and observe them. Mars's river valleys were carved by flowing water at a time when Earth's continents were still forming, before the first plants colonized the land, before the first animals crawled from the seas. Those ancient Martian rivers dried up billions of years ago, and the planet has been a desert ever since, slowly losing its atmosphere to space, grain by grain, molecule by molecule, waiting through the ages in cold stillness. Jupiter's great red spot has been raging for at least 3 centuries, possibly much longer. This single storm is older than the United States, older than the scientific revolution, older than the printing press. It has spun in Jupiter's atmosphere through all of human industrial history, indifferent to our rise from agrarian societies to spacefaring civilization. And it may continue for centuries more, or it may finally dissipate in the coming decades. Even planetary features that seem eternal are temporary on the timescale of the solar system. Saturn's rings, those magnificent structures that make the planet so instantly recognizable, may be relatively young in cosmic terms. Perhaps only a few 100 million years old. This means they might not have existed when dinosaurs first walked the Earth, and they're slowly disappearing, raining down onto Saturn's upper atmosphere at a rate that suggests they may be gone in another few 100 million years. We're living in a special time, a window of cosmic history when Saturn has its rings. beings who inhabit Earth hundreds of millions of years from now, if such beings exist, may look up and see a ringless Saturn, and they'll never know the beauty we've been privileged to witness. The moons we've encountered each have their own tales to tell. Europa's subsurface ocean has potentially been liquid for billions of years, isolated beneath kilometers of ice, possibly harboring life that evolved entirely independently of Earth. If life exists there, it would tell us that the emergence of life is not a unique cosmic accident, but a common outcome. When conditions are right, a discovery that would fundamentally change our understanding of our place in the universe. Enceladus, tiny Enceladus, smaller than the width of Texas, somehow maintains a liquid ocean beneath its icy shell and powers geysers that shoot water into space. The energy for this activity comes from tidal heating, the same force that makes Io volcanic. But the fact that such a small world can remain geologically active billions of years after its formation reminds us that the solar system is full of surprises, that small worlds can be just as dynamic and interesting as large ones. Titan, with its thick atmosphere and liquid hydrocarbon lakes, shows us that familiar patterns can emerge from alien chemistry. On Titan, methane and ethene play the role that water plays on Earth, forming clouds and rain, carving river channels, filling lakes and seas. It's a world that's bizarrely familiar and utterly alien at the same time. A reminder that the universe is more creative than our imaginations, that nature finds ways to create complexity under conditions we might have thought impossible. The asteroid belt, that collection of millions of rocky fragments, represents the planet that never was. If Jupiter hadn't formed where it did, if its gravity hadn't stirred up the orbits of planetesimals in that region, those fragments might have accreted into another rocky world, perhaps one that could have harbored life. Instead, they remain scattered, frozen in time, permanent witnesses to a planetary formation process interrupted. Every one of those asteroids is a world unto itself, with its own craters, its own composition, its own history of collisions and near misses stretching back to the dawn of the solar system. And what of the comets, those icy visitors from the outer reaches? They spend most of their lives in the cold darkness beyond Neptune, or in the even more distant Oort cloud. Frozen worlds where the sun is just another star in the sky, but their elongated orbits occasionally bring them into the inner solar system, where the sun's heat vaporizes their ices and creates those magnificent tales that have inspired wonder and sometimes fear in humans throughout history. Each comet is a messenger from the outer darkness, bringing with it pristine samples of the material from which the solar system formed, virtually unchanged over billions of years. The cosmic perspective we've gained from this journey is both humbling and empowering. We're humbled by the scale, by the age, by the realization that human history is less than an eye blink in the life of the solar system. All of our civilizations, all of our wars and discoveries and artistic achievements, all of the lives ever lived, have occupied a tiny sliver of time on a tiny speck of rock orbiting an ordinary star. But we're also empowered by the knowledge that we, alone among the species we know of, can comprehend this perspective. We can send machines to other worlds. We can decode the light from distant stars. We can understand the laws that govern the motion of planets and the evolution of stars. We are, in a sense, the universe becoming conscious of itself, matter that has organized in such a way that it can ponder its own origins and nature. This dual realization, our insignificance and our uniqueness, creates a profound sense of peace. Our worries are small. Yes, insignificant against the cosmic scale. That argument you had, that mistake you made, that embarrassment that keeps you up at night, none of it will matter in 100 years, let alone in the billions of years that stretch ahead for our solar system. This isn't nihilism. It's liberation. If our troubles are cosmic ally insignificant, then we're free to let them go, to release the anxiety that serves no purpose. At the same time, our existence is precious precisely because of its improbability. Of all the worlds we visited, only one, Earth, harbors life and consciousness. That makes every living thing on our planet valuable, every moment of consciousness precious. We are rare, perhaps vanishingly so in the cosmos, and that rarity gives meaning to our existence even in an indifferent universe. As we float here between worlds, we can appreciate both truths simultaneously. We are small and temporary, yes, but we are also remarkable and precious. We are dust that thinks, matter that dreams, atoms, arranged in such a way that they can contemplate the stars from which they came. This paradox, this tension between insignificance and significance, is at the heart of the cosmic perspective, and in embracing both sides of it, we find a deeper peace than either alone could provide. The solar system itself offers lessons about balance and harmony. Despite the chaos of its formation, despite billions of years of collisions and near misses, it has settled into a stable configuration. The planets orbit in regular patterns, their motions predictable centuries in advance. This order emerged not from conscious design, but from the interplay of physical forces, from gravity and momentum and conservation of energy. It's a reminder that balance and stability can emerge naturally from seeming chaos, that systems tend toward equilibrium given enough time. Yet within this overall stability, there is constant change. Mountains rise and erode. Atmospheres evolve. Orbits slowly shift. The solar system of 4 billion years ago was different from today's, and the solar system 4 billion years hence will be different still. Change and stability coexist, each on its own timescale. This too is a lesson, that we can find stability in our lives while also accepting and embracing change. That permanence and flux are not opposites, but complementary aspects of existence. The journey we've taken through the solar system is, in a sense, a journey through ourselves. We are made of stardust, literally. The atoms in your body, except for the hydrogen, were forged in the hearts of massive stars that exploded billions of years ago, scattering their enriched material into space. That material eventually coalesced into our solar system, into the Earth, and eventually into you. When you look at the stars, you're looking at your distant ancestors. When you breathe, you're inhaling atoms that might once have been part of a dying star's outer envelope. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces and distributed by stellar deaths. This connection to the cosmos is not metaphorical but literal. You are not in the universe, you are of the universe. You are a way that the universe has found to experience itself, to know itself, to appreciate its own existence. This realization can fundamentally shift how you see yourself and your place in the grand scheme of things. You are not separate from nature, watching from outside. You are nature, experiencing itself from the inside. As we prepare to fully return from our journey, to bring our consciousness back to our familiar surroundings, we carry with us this expanded perspective. The problems and pressures of daily life await, yes, but they are now contextualized within something much larger. When you feel stressed or anxious, you can remember the view from space, the sight of Earth as a tiny blue dot, the vast distances between worlds, the patient turning of planets in their orbits. You can remember that the universe is old and large, that countless beings have lived and died on Earth before you, and countless more will come after. Your individual struggles are part of a larger human experience, which is itself part of an even larger cosmic story. This context doesn't make your life less meaningful. It makes it more so. Because you can see how your small part fits into the larger whole. The peace you felt floating among the planets is always available to you. It's not dependent on external circumstances. It comes from perspective, from the ability to zoom out and see your life and your world in context. When you're caught up in the details, when the small things seem overwhelming, you can practice zooming out. Imagine yourself rising above your immediate situation, above your city, above your country, above the Earth itself, out into space where you can see our planet as one small world among many. From that vantage point, your problems don't disappear, but they become more manageable. You can see them as temporary fluctuations, minor perturbations in the overall flow of your life. You can respond to them with more calm and wisdom, because you're not completely identified with them. You're aware of them, yes, but you're also aware of the larger context in which they exist. This cosmic perspective also connects you to something larger than yourself. When you look up at the night sky, you're not just seeing distant lights. You're seeing actual places, real worlds with their own landscapes and features. Some of those points of light are planets in our own solar system, worlds we've visited on this journey. Others are stars, some of which have their own planets, their own systems, and beyond them are galaxies, each containing hundreds of billions of stars, stretching out to the very edges of the observable universe. You are part of this vast cosmic web. The photons entering your eyes traveled across space to reach you. The gravitational pull of the moon tugs on you, microscopically small but real. The solar wind that flows from the sun interacts with Earth's magnetic field to create the auroras, and that same wind fills the entire solar system, connecting all the planets in a tenuous but real way. You are not isolated but connected, part of an intricate network that spans the cosmos. This connection can be a source of comfort, even in moments of loneliness or isolation. You can remember that you're part of something vast and ancient, that the atoms in your body have been recycled through multiple generations of stars, that you breathe the same air that was breathed by every human who ever lived, that you see the same moon and sun that have been observed by countless generations before you. You are connected through time and space to all of humanity and to the cosmos itself. As the solar system continues its ancient dance, as the planets orbit and the moons circle and the sun steadily burns its fuel, you too continue your journey through life. But now, having taken this tour, having seen the cosmic context, you move forward with a different understanding. You understand that your time is limited but precious, that your problems are temporary, but your existence is significant, that you are small but connected to something vast. This understanding brings peace, not a peace that comes from having no problems, but a peace that comes from seeing problems in their proper context. Not a peace that comes from avoiding challenges, but a peace that comes from facing them with wisdom and perspective. Not a peace that comes from isolation, but a peace that comes from recognizing your connection to the larger whole. The solar system has been a teacher on this journey, showing us through its example how beauty, order, and peace can emerge from natural processes. It shows us that vast scales of time and space, rather than making life meaningless, actually provide the context that makes meaning possible. It shows us that we are both insignificant specks and remarkable cosmic achievements, and that both perspectives are true and valuable. As you return fully now to your immediate surroundings, as you feel your body once again, as you prepare to rejoin the world of daily concerns and responsibilities, you bring with you the gift of perspective. The cosmos is always there, always available whenever you need to remember the larger context. The peace of space, the silence between worlds, the patient orbits of planets, these are not just out there, but also within you, part of your awareness, part of how you can choose to see the world. Rest now in this peace, this cosmic calm that comes from understanding your place in the universe. Let the journey settle into your consciousness. Let the images and feelings integrate into your awareness. You have traveled billions of miles in your mind, visited worlds beyond imagining, witnessed the majesty of our cosmic neighborhood. Carry this experience with you as you return to your life and let it inform how you see yourself and your world. The tour is complete. The journey has given you its gifts. Now there is only the gentle return to rest, to sleep, to dreams perhaps colored by the images of distant worlds and cosmic vistas. Float in this peaceful space between waking and sleeping, between Earth and the stars, and let consciousness gently fade into the restorative darkness of sleep. The solar system continues its eternal dance, and you are part of that dance, a conscious participant in the cosmic story. Rest peacefully, space traveler, knowing that you are exactly where you need to be, a perfect part of a perfect universe, small but significant, temporary but precious, alone but connected to everything that is. Sweet dreams, and may your rest be as peaceful as the silence of space, as deep as the cosmic night, as renewing as the eternal cycles of the planets around the sun.